Alright, lecture 4.2 out of 3 for the probability unit. So this is over conditional probability. And before we discuss conditional probability, we got to discuss what it means for two events to be independent. So two events are independent if the occurrence of one does not affect the probability of the other. So, let's look at some examples here. Number one, drawing a king, then drawing a queen. Are these independent? Suppose I have a deck of cards. I draw a king. Suppose that happens. Pretend that happens. Does that affect the chances of me of drawing a queen? The answer is yes, which means these are dependent. Because the moment you draw a king from the deck, you have changed the deck of cards. There's no longer 52 cards in that deck. You have thus changed the probability of getting that queen. So if you draw a king, the probability of you getting a queen on the next draw is a little bit higher, because now there's 51 cards in the deck instead of 52. Now, what about you roll a dice? Suppose you roll a 3, then roll a 2. Are those dependent or independent? Well, those are completely independent. One dice roll does not affect any other dice roll. So dice rolls are always independent. So it doesn't matter what you roll, that whatever you get on the first roll will not affect the second roll. What happens if I draw a marble from a bag? If I take a marble out of a bag, does that affect the probability on my second draw? Well, yes, it does. It's just like the card example. These are dependent events. Alright, because what's the probability of drawing 2 red marbles in a row? Well, the moment I draw a red marble on the first draw, the chances of me getting another red marble are a little bit lower because I've taken one of those red marbles out of the bag, which has a finite number of marbles. And what about getting heads twice in a row? Well, that is independent. Naturally, coin tosses are going to be independent of each other. They do not affect each other. So that's the idea of independent versus dependent. Which brings us to conditional probabilities. So, if you look here, that's where we got the notation, probability of B given A. And anytime we are computing probability for a sequence of events, we use multiplication, and we always assume the previous event has occurred. Otherwise, it's over. So, compute the probability of rolling even 3 times in a row. So, on the first roll, what's the probability you roll even? Well, that would be 3 out of 6 on the first roll, and then we multiply. What about rolling even on the second roll, assuming you got even on the first roll? Well, these are all independent, so they don't affect each other, so it's again 3 out of 6. Pretend you do get an even. What's the probability of getting another even on the third roll? Well, that's also going to be 3 out of 6. And we can reduce all those fractions. That's 1/2 times 1/2 times 1/2, which is 1/8 is the answer. Now, let's look at a more interesting example where events are dependent, because that will affect the probability computation. Determine the probability of drawing 2 hearts in a row. So let's go with the first draw. So there's 13 out of 52 cards that are hearts. And that's your first draw. Time to do the second draw. So pretend your first draw was one of the hearts. So whenever you're doing a sequence of events, you always assume the previous event occurred. So pretend you got a heart on the first draw. Otherwise, the sequence won't be done. So there's now 51 cards in the deck, because you took one out. And out of those 51 cards, how many left are hearts? Well, that would be 12. There were 13 hearts, but remember, you took one of the hearts in the first draw. So here we'll need a calculator. So 13 times 12 is 156. Divided by 52 times 51 is 2652. And we can go ahead and reduce that fraction. And that reduces to 1 in 17. So you have a 1 out of 17 chance of drawing 2 hearts in a row. Alright, what about drawing a king, then a queen? These are, again, dependent events. So we'll start with the king. So what's the probability you draw a king? Well, there's 4 kings out of 52 cards. So that's the first draw. Now you always assume that that occurred. So pretend you took one of those kings out of the deck. How many cards are left? Well, there's now 51 cards left in the deck. Out of those 51 cards left in the deck, how many of them are queens? Well, there's still 4 queens left in the deck. We haven't removed any. And then you multiply accordingly. So that's 16 out of 26, 52, which is going to be, when we reduce, going to compute that real quick, 4 out of 663 is the answer there. And let's look at another example. We got a 3-person jury must be randomly selected from a pool of 6 men and 6 women. Compute the probability of an all-female jury. So you just got to pick them one at a time. So let's go ahead and pick our first person for jury duty, and we're going to assume it's all female. So what's the probability? The first person you pick is a woman. Well, there are 6 women out of 12 people. All right. So that's the probability you get a woman on the first draw. Now, what's the probability you get a woman on the second draw, assuming you got a woman on the first draw? So there's now 11 people left in the pool. And how many are female? Well, 5 out of those 11 are female, because remember, we took 1 in the previous draw. And then we go again. So then you ask yourself, okay, well, how many are left now? There's now 10 people left to choose from, and how many of those are female? Well, there are 4 females left. So you compute all that. 6 times 5 times 4 is 120 out of 12 times 11 times 10 out of 1320, and that does reduce. We'll go ahead and reduce that down. And that reduces to 1 out of 11. So there's a 1 out of 11 chance that you randomly select an all-female jury in this case. Alright, enough about juries. Let's talk about chocolates. Something I'm quite fond of. So we got a box of chocolates. Contains 6 milk chocolates, 5 dark chocolates, and 3 white chocolates. What's the probability of drawing a dark chocolate or a milk chocolate? And I stress this word right here, or. So we are not doing multiple drawings here. We're doing one drawing. One single drawing. So that means we do not use multiplication. We only use multiplication for a sequence of events. This is not a sequence of events. This is a singular event. So what's the probability of drawing a dark chocolate or a milk chocolate? Well, there's 5 dark chocolates out of, 8 plus 6, 14. So 5 out of 14 are dark chocolates, plus, for milk chocolates, that would be 6 out of 14 are milk chocolates. And there is no overlap there. So this problem is straight out of the last pen cast. So if it's an OR probability, so make sure you read carefully. If it's an OR probability, you're basically using addition and subtraction. Right? In the event there's overlap. Now, if we look here in part B, this says then. So going back up here, this is where you're going to add / subtract probabilities. This is where you're going to multiply probabilities. So make sure you read carefully. So compute probability of randomly drawing a dark chocolate, then a milk chocolate. So by changing one word in the problem, I've completely changed the mathematics. So probability of drawing a dark chocolate is 5 out of 14, and here we're using multiplication, not addition, because it is a sequence of events. Now, whenever you have a sequence of events, you always assume the previous event occurred, so pretend you got a dark chocolate. Now you're going to draw again. Well, what's the probability that your second chocolate is a milk chocolate? Well, how many chocolates are left in the box? There's 13 chocolates left in the box, and how many of those 13 chocolates are milk chocolates? Well, we haven't touched any of the milk chocolates yet, so all 6 still remain. We multiply accordingly. So that's going to be 30 out of 14 times 13. Let's go ahead and compute that. Which is 182. We can go ahead and reduce that. 30 divided by 182, and that'll reduce down to 15 over 91. Please make sure you're always reducing all your fractions. Alright, so quick warning here. Make sure you know when to use addition. So that's going to be an OR probability versus when to multiply. And you're going to multiply probabilities if it's a sequence of events. So it's very important that you don't mix those up. Let us go ahead and look at the at least once rule. So last topic for this pencast. So the at least once rule states if all attempts are independent. It's very important this rule only applies if the trials are all independent. Assuming they're all independent, then the probability of event E occurring at least once in n attempts is given by 1 minus the probability E does not occur in a single trial raised to the n power. So basically, it's using that not probability, the probability of an event not occurring, which we discussed in the previous pencast. So if we want to figure out the probability of something not happening, we subtract from 100%. Well, what's the opposite of not happening at least once? Well, that would be not happening at all. So compute probability of rolling at least 1 3 in 5 attempts. So the opposite of not getting a 3 at least once is never getting a 3. So you do 100% minus what's the probability you do not get a 3. Well, if you're rolling a 6-sided dice, the chances that you don't land on 3 are 5 out of 6. And what about on the second roll? Still 5 out of 6. What about on the third roll? 5 out of 6. What about on the fourth roll? 5 out of 6. What about on the fifth roll? Well, still 5 out of 6. So in other words, you can type that into your calculator like this. 5 out of 6 in 5 attempts. And we'll go ahead and type that into the calculator. So 1 minus 5 out of 6 raised to the fifth, and we get approximately 59.81%. So you almost have a 60% chance that if you roll a dice 5 times, you get at least 1 3 in there. Maybe, and when I say at least 1 3, it's just that at least 1, maybe multiple times, but at least 1. All right. So here's one of my favorite probability questions. So a single scratcher ticket has a 1 in 5 chance of winning, right? You see these at the gas stations. 1 in 5 is a winner. So you're clever, like, oh, 1 in 5 is a winner. I'll buy 5 tickets, then I'll be a winner, right? Well, if you've done this before, you may have been disappointed. Let's compute the actual probability that you have at least 1 winning ticket if you buy 5 of these things. So naturally, these lottery tickets and scratcher tickets, they're all independent of each other. So we can use the formula, the at least once formula. So, at least 1, that right there gives away you're using this formula. So that's 1 minus. Now, what's the probability that the ticket is a losing ticket? So, well, you have a 4 out of 5 chance that it's a losing ticket. And how many did we buy? Well, we bought 5 of them. So we'll go ahead and compute that probability. And let's see here. 1 minus 4/5 raised to the 5th. You get approximately 67.23%. So no, it's not guaranteed that if you buy 5 scratcher tickets and 1 in 5 is a winner, you're not guaranteed to have a winner. And you might think, well, that's false advertising. No, it's not false advertising. It's just understanding probability. Now, you have a a good shot at having at least one winner. But as you can see, with a 67% probability, it's definitely not guaranteed. Alright, last example. So, what is the probability of drawing at least one king in 4 attempts? Gotta be careful here. Warning, these events are not independent. They are not independent, so we can't use the formula. We got to do it manually. So the opposite of getting at least one king is never getting a king. So we take the opposite, subtract it from 100% to get the corresponding probability. So we're going to do 4 attempts, and the opposite of at least one king is never getting a king. So what's the probability that your first card you draw is not a king? Well, that would be 48 out of 52. All right, 48 of the cards out of 52 are not kings. Times, suppose you do not get a king on the first draw. What's the probability you do not get a king on the second draw? So there's now 51 cards left in the deck. How many of them are not kings? Well, that would be 47 out of 51 are not kings. Alright, let's do it again. So third draw, there's now 50 cards left in the deck. How many of them are non-kings? That's 46. Alright, every single draw we're removing one of the non-kings. And then our fourth and final draw, there's now 49 cards left in the deck. And of those 49, 45 of them are non-kings. So let's go ahead and punch this into the calculator. So if you're typing this into your calculator, you'll need to be very careful with parentheses. Alright, unless your calculator has a parentheses feature, you need, a fraction button. You'll want to keep all these fractions in parentheses. Let me type it in real quick. Stand by. Typing in the last fraction now, and you get approximately, let's see here, a 28.13% chance. So you have almost a 30% chance that if you draw 4 cards, at least one of them is a king. And I want to go ahead and add an extra example here. A bag of, let's say, 30 marbles contains 2 red marbles. So out of those 30 marbles in the bag, 2 of them are red. Compute probability of drawing 3 red marbles in a row. Now, you don't have to do any math if you're clever here. You don't have to do any computations if you have a basic understanding of probability. You know the probability here is 0. This is impossible. There's only 2 red marbles in the bag. Therefore, it's impossible to get 3 red marbles in a row. Well, let's see if the math backs that up. So on the first draw, what's the probability you get a red marble? Well, there's 2 out of 30. Okay, so remember it's a sequence of events, so we use multiplication, and we always assume the previous occurs. So, assuming your first marble's red, there's now 29 marbles left in the bag. How many of them are red? Well, that's 1. And then let's do our third draw. Now there's 28 marbles in the bag, and how many of them are red? Well, 0. And what's so special about 0? Well, if you multiply anything by 0, it's automatically 0, which makes sense. There's a 0% chance that you can get 3 red marbles in a row if there's only 2 in the bag. And that's a wrap. So keep up the hard work, guys, and don't be afraid to contact me if you have any questions. And don't be afraid to get tutoring from the Academic Success Center if you need assistance. Have a wonderful day.